This section of the appendix 44.11 is on scalars, vectors, matrices, tensors, and in general, all of these are really tensors of different ranks, along with linear algebra and some matrix theory. Now, much of this is covered in other places, but it's nice just to bring it together in one place. What is a scalar? Scalar is defined by a single real number: time, temperature, mass, volume, energy. These do not point in one direction or another, and they're specified by a given value. So we call these scalars, single numbers. A vector, on the other hand, is an ordered n-tuple of real numbers, like x, y, z, or x1, x2, x3. An example of a vector is 1, minus 5, 0. Longitude, latitude, and altitude give us our position in 3 dimensions, whereas longitude and latitude is a vector in 2 dimensions because it has 2 numbers that are needed to specify a point. And in general, we've talked several times about the fact that the dimensionality of a space is the number of numbers needed to specify a point. A vector in that space is going to have that many ordered numbers in its specification. Examples of vectors are position, velocity, acceleration, force, momentum. I mean, you can't have a force unless it's a value like 6 newtons and it points in a given direction. You can't push on something without pushing in a direction. You can't have a velocity without something going in a particular direction, and likewise a momentum. The components of a vector must transform exactly like the coordinates in a transformation. Many people forget to tell you this, but I can't just write down 3 numbers like 1, 2, 3 and say, oh, that's a vector. If I say that this is a vector, it means that if I transform the coordinates of the space by some transformation to new values, x prime, y prime, and z prime, these 3 numbers must transform to 3 new numbers exactly as these values transform. In other words, they must undergo the same transformation. I can't just pick out 3 things like your height, your weight, and your shoe size and say that's a vector. That's absolutely meaningless. That's just a set of 3 numbers. So I hope you understand, because this is critically important and most people do not mention it. The textbooks or in lectures. The vector components must transform exactly as the coordinates of a vector, of the coordinate vector in that space. Now we can also have a matrix. So we can have a scalar, which has 1 component, a vector which has n components in n dimensions, and a matrix. And a matrix can, of course, be an n by m matrix, but in general, it's going to be an array in n dimensions that's going to have n by n dimensions. It's going to be a square matrix in a space. It doesn't have to be. For example, we could look at what is used in network theory, a connection matrix, Cij. These matrices are very interesting because they give you the connection between I and j. This might be airports 1, 2, and 3, 1, 2, and 3, and how many flights go from one airport to another. This particular type of matrix always has zeros on the diagonal, or a meaningless number, in other words, just a blank. And then from airport 1 to airport 2 might have 8 flights a week. From 1 to 3 might have 1 flight a week. From 3 to 1, it might have 2 flights. This might be 7 flights. And from 2 to 3, I might have 4 flights a week, and 4 flights over there and 4 flights back. So it may or may not be symmetric. An array like this of numbers, which looks like a set of vectors, is called a matrix, or 2-dimensional array. It's indexed with 2 indices. You'll see here I talk about Cij. This is given as the row. This is given as the column. So this would be, for example, C12 means the first row and the second column. So this would equal to 8. Whereas up here, we write this vector with equivalently as a set xi. And we could say xi is x1, x2, x3, rather than using x, y, and z. And so we could say x2 was equal to 6, meaning that the second coordinate was equal to 6, or in other words, y. A matrix is often used to perform a linear transformation on a vector. That's the basic study of linear algebra. If I have a vector 1, 2, 0, 0, 1, 1, 2, 2, 2, and I let that act on a vector of 1, 2, and 1, then the way that you compute the result of this transformation, or matrix times a vector, or even a matrix times another matrix, is you take the first row and take the dot product of this vector with this vector here. So you'd take 1 times 1, which is 1, plus 2 times 2, which is 4, plus 0 times 1, which is 0, and that's 4, 5, so this number is 5. Then I would take this times this, dot product, 0 times 1, 0, 1 times 2 is 2, 1 times 1 is 1, so I get 2 plus 1, which would give me 3. Then I have 2, 2, and 2, that would give me 2, 4, and 2. That would give me 8. And this is the transformed vector. This is the transforming transformation. So I have a vector 1, and have a transformation, and have a vector 2. So this is how the transformation works. If I perform another transformation, then this is like a composite transformation, and I can take two matrices, I multiply this by this, this, and this, then this by this, this, and this by this, this, and this, each time taking a dot product, and I would get, as I go across here, 1, 2, 3, I'd get this, 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 then I would get, using this one, this, 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 then using this one times these three, this, this, and this, exactly in the same manner. So the product of two transformations is in itself a transformation. We can use those to solve linear equations. One example, good example of a transformation is a rotation. Cosine theta minus sine theta, cosine theta. And when this acts on a vector, like x and y, it transforms x and y and moves it around to a new x and a new y that's rotated. So for example, a point here is then rotated to a new point here. This is xy, this is x prime, y prime. So transformations can rotate vectors. Sometimes matrices can commute with one another. A times B is the same as B times A, but sometimes they're different. So this is an important operation. Matrix A times matrix B minus matrix B times matrix A. And if they're different, this is called a commutator. It's a special type of product, and it's used frequently with matrices. A scalar, I should get some new paper here. Call this A, so this would be 44.11b. A scalar is, in fact, a tensor of rank 0. A vector is a tensor of rank 1. A matrix is a tensor of rank 2. And we can have tensors of any rank. In fact, if we take some object, like A, if it has no indices, it's a scalar. If it has one index, it's a vector. If it has two indices, it's a matrix. If it has three indices, it's a tensor of rank 3. So the number of indices that I have is in fact the rank of the tensor. And scalars and vectors and matrices are just the 0th, 1st, 2nd, and 2nd of those types that we might have. Now we've talked about operations with vectors like we used in high school. And if you have a vector A and another vector B, then you can add the two by completing a parallelogram. So this is the vector A plus B. And that graphical knowledge is very useful, but in picturing the vectors. But other than that, it's not very useful in a practical sense, because normally these vectors are in 3 dimensions or 5 dimensions, and therefore you can't do this. If I have a vector minus b, I can talk about a minus b as the vector a plus the vector minus b. And A plus the vector minus B is just the vector right here. This is A minus B. It's the vector A plus the vector minus B, and the vector minus B just goes in the opposite direction of B. So I can take a vector A and I can add another vector or subtract another vector. And I can also take a vector A and multiply it by a number. Like I can take 4 times A. That would be a vector 4 times this long. That's A, and points in the same direction. It doesn't look quite 4 times as long, we'll make it like that. There are some unit vectors, unit I, unit J, and unit K, that are used sometimes in engineering. And those vectors are used to represent little tiny vectors I, J, and K in a coordinate system. And therefore, this vector is written as something like 6 times I plus, we put a hat on this to indicate a unit vector, plus 3 times J plus 4 times K. And this is a vector R. And it's the sum of this, this, and this, and therefore it's off in space here somewhere. This is an awkward way to deal with it. These IJs and Ks are totally unnecessary. It is much better to write R as 6, 3, 4. This is the component form. And likewise, we can write this, oops, my paper got off there, 6, 3, 4. And I can write these components as X, Y, and Z, but a still more sophisticated representation is use X1, X2, and X3. That way I don't use up as many letters. So we often use that component form, and we can talk about the vector R, or we can talk about a vector Xi, or Xi, meaning we just use the set of components, which are X1, X2, and X3, meaning that this is a set. So that's the way we write vectors, and we can talk about a vector R in either way or simply as Xi. And for example, we can write it this way. If we write it this way, it's very fast to add and multiply. So if you have a vector, like let's say this vector, 3 minus 2, 5, and I want to add a vector 1, 0, 1 to that vector. Add that vector, I just get 4 minus 2, 6. Fast as lightning. So I've added these two vectors. I could likewise subtract this vector. And if I subtracted them, I would get the vector 2 minus 2, 4. I can also take a vector like this one and multiply it by 2, by some value. And then I would get 2 times, let's call that the vector A. If I take 2 times A, I would just have 6 minus 4 and 10. So you can see that the operations on a vector are very fast when written in a component form. I want to talk now about the difference between a linear vector space and a metric space. To do that, I'm going to move this paper up a little bit higher. So we can read it, and I'm also going to start with a new piece of paper here, because this is an important concept. This is 4411C, the third page of this discussion, on vectors, matrices, scalars, tensors, linear algebra, and so forth. If I have vectors, and I can add them, and subtract them, and I can multiply them by a number, then such objects form what is called a linear vector space, LVS, linear vector space. Two operations, I add two vectors and I get another vector. I take a vector times a number and I get another vector. I can also see that that there is normally a set of vectors which are independent of each other. Let's say in 3 dimensions, there might be 3 of these, and I could take a number alpha 1 times this plus alpha 2 times this plus alpha 3 times that and represent some other vector, vector D. So the vector D is characterized by alpha times this vector plus beta, alpha 1 times this, beta alpha 2 times that, and alpha 3 times that. Alpha 1, alpha 2, and alpha 3 are often called the components of the vector in a basis where I've used A, B, and C. Now if A, B, and C, if this is A, B, and C, are just some vectors, then it's kind of difficult to deal with these numbers in a good way. We really would like to have the vectors A, B, and C all perpendicular to each other and of unit length. That will make things much, much nicer. So normally we're going to think of our vectors where the components are with respect to a basis, where the basis is what is called orthonormal. That means they're orthogonal to each other at right angles and normal. But in fact, we have a linear vector space. If we just write a vector as a combination of other vectors that are linearly independent of one another. What is a linear vector space? A set of objects that I can add and subtract, or I can multiply by number, and I get closure in the space. It has n dimensions if there are a fundamental set of n of those objects, such that every vector in the space can be represented as a set of numbers times those vectors added up. Do you have a sense of what a linear vector space is now? Turns out that a linear vector space is not very powerful. It's not powerful because I really don't have a sense of geometry for it. A sense of geometry means that I can do angles and I can do length. And this requires the dot product, or sometimes called the scalar product. And the scalar product, and now I'm going to assume that I'm going to use a basis for my vectors that's orthonormal, because I can talk about orthonormality. I can require that A, B, and C all be perpendicular to one another. And so I form a new kind of product, vector A dotted with vector B, and this is by definition A1 times B1 plus A2 times B2 plus A3 times B3, and I keep on going depending upon how many components there are in the space. So I could write it as the sum over I of AI BI, meaning I take the product of the first two and add that to the product of the second two and so forth. That gives me the dot product. Now the powerful thing is the dot product is equal to the magnitude of the first vector times the magnitude of the second times the cosine of the angle between them. So there are two things that follow from that immediately. Number one, I can take a vector A dotted with itself. And if I do, I can see that that's the length of the vector A times the length of the vector A times the cosine of the angle between A and A. But that angle is 0, the cosine is 1, so this becomes A squared. So the length of a vector is the square root of A dot A. And lo and behold, since that's A1 times A1 plus A2 times A2 plus A3 times A3, this is the Pythagorean theorem in n dimensions that we've just arrived. It's also the way to find the length of a vector. So we've got length, and now we also have angle. So given two vectors, I can find the length of A, then the length of B, take the dot with the dot product, then take A dot B, divide by the length of A and the length of B, and I get the cosine of the angle. So I get the cosine, the angle between A and B is going to be the inverse cosine of A dot B divided by the length of A times the length of B. And now I have length and I have angle, the Pythagorean theorem, and this theorem here. And now I can do all kinds of geometry, even in n dimensions. In 7 dimensions, I can now find the angle between two vectors and the length of a vector. And so that's very powerful. A linear vector space that has a dot product, such as this, is called a metric space. It's called a metric space because this product here lets you take that space, takes that linear vector space, and find length and angle and therefore you have metrics on the space. In general, we can use a more powerful form of a metric on a space, such as is used in curved spaces and curved space-time in general relativity, and not just take the regular dot product here, but put a matrix right here. And in doing that, we take A dot B and use a metric like G mu nu, A mu, B nu, summed over mu and nu, for however big it is, and this can not only be a set of constants, this can even be a function. So it can differ from one place to another and actually give you spaces that have curvature and other forms.